Hello everyone, it's Carter from 19. Today is day 38 in my challenge day. And what I'm going to learn is about the ray tracing series in the light scattering section. And in the last weekend, that I didn't record the videos, but I just learned some about the basics of light scattering and the scattering PDF. And the new concepts that I learned is a solid angle that we can use in three-dimensional spaces. So originally we are only used the radians, which is the zero dimension angle that we can use in the one dimensional axis. But in the three-dimensional cases, we need another angle that can be represented as a surface area on the sphere. So in this case, we can follow these um, equation for the solid angle there. But I'm going to skip the derivation of how I get this, how we can get this solid angle exactly. The next things that we have to know that is the albedo. The albedo is called a whiteness in computer graphics, and this is depends on the is used to define some form of fractional reflectance. And the fractional reflectance vary with the color and incident direction. And incident direction means that the direction of incoming ray on the specific surface. So for example, we have this kind of surface, and the incident direction means that the incoming ray to this surface before this ray outgoing from this surface. So that's exactly the incident direction means. Raising this fraction, for instance, we want to. And a very important concept newly added in this section from this section is about photon. The photon, um, so actually we can view the light as a two perspective, which is the one is the photon, and the another is some wavelength like characteristics. And the energy of the photon we can represent it and follow this equation where the h is Planck constant, v is a frequency, and the c is this is well, a lambda is a wave length. Okay, so each individual photon has a tiny amount of energy, but and the absorption or a scattering of a photon is probabilistically determined by the albedo of an object. So by so far, we represent the color as the RGB format. In the rear PBR renderers, we would use a predefined set of the specific wavelengths for the light color. As you can see here, as 300 nanometers and 350 nanometer and 700 nanometer and so on. And also the human visual systems mm, can accept the set of colors. Uh, this is also kind of similar to RGB because they are mainly uh, accept the RGB color, the actual exactly it's not same with the RSB. By skipping this some characteristics of PDF scattering PDF, the outgoing color against the incoming ray that that is exactly same with this equation. So A is equal to albedo, and the P scatter is scattering PDF, and the color is a specific color from about the incoming ray, incident direction. So if we take an integral of this whole the whole this multiplication, then we can get the single outgoing color, which is scattered from the surface. And the real application, we can do that. We can we can take the infinity integral because of the limit of computational power. So we have to use some kind of limits of the sum boundaries like this. Color will be approximated to the sum of these equation, and we are going to divide these by the PDF. And this PDF is different to PDF scattering PDF. And this PDF is the whatever going direction is we randomly generate. And for a Rambertian surface, which is the ideal diffuse surface, we p scatter can be replaced with the cosine density, which is the cosine rule. The cosine rule is simply um, the more the result of dot product between the incoming rays and the normal vector of the surface is higher, the more brightness going up. That's the exactly rule of the cosine rule. And we can get the differential area on the hemisphere can be derived by this following image. So this line is radius, and this radius is apart from a theta angle by the vertical axis, and this is xy plane. Mhm. And if we project this onto this xy plane, this right side of this projected area is theta phi, and this is a small angle differential. It's a differential of phi, and this side is a differential of theta because it has the same direction. And the d theta, d phi is only d phi when the radius is exactly same with the r. But in this case, if we projected um, this vector onto this xy plane, it's not this r because we have to compute by the sine theta. So in this case, the length of this arc is equal to sine theta d phi by multiplying d phi with the sine theta. So we get the sine this uh, we get this length, this arc length, and this arc length. If we multiply, we have a differential area. That's what exactly we do in on the Lambertian surface. And the technically correct standard reflection is defined by the BRDF model, and the shortly the bidirectional reflectance distribution function. So p scatter we get by using this derivation, we get the p scatter is equal to this cosine theta output over phi. So if we substitute the p scatter with this equation, then we got this PRDA is simply the A over phi. Okay, this is end up of the things that I learned on this weekend, on the last weekend. And now let's start. So okay, I learned the most things that I learned today. Actually, this is not enough amount of learning today, but let's recap. Anyways, so we learned the importance sampling and about the light scattering using the PDF in the previous sections. And then it's time to apply the those concepts into our application from now on. So we need to assume that we have some kind of PDFs like P light toward PDF and the P scatter or the PDF the scattering and the P surface. This PDF is related to P scatter. And one of the good things that of PDF that even though we mix two PDF, it still can be a PDF which is forms the mixture densities. For example, we can combine the P surface and the P light with the weight of 1/2 um, to generate another PDF that forms mixture densities. And this is also PDF. But this fact is only kept when the weights, in this case, is 1/2, and the right side 1/2 is the weights of mixing equation. When they are positive and they are add up to the 1, they can be the result can be a PDF. But for example, if the weight is minus, they it to break a rule of the PDF. And also, if they are not add up to, they doesn't add up to the 1. This is also not PDF because the integral of PDF will not be the 1, and this is not probability. So our mission is to figure out how to make the PDF larger, where the product of p scatter and color is largest. And there's a two case. The for diffuse surface like Lambertian surface, by following the cosine rule, let's assume that we have a surface like this, and there is a normal vector on above this surface. And if the where is the largest these dot product is exactly when the normal vector direction and the scattering direction is same. When the outgoing direction is going to light, that is the largest cosine. Um, with that reason, the guessing where color I is the largest is equivalent to guess where the most light is coming from. On the other hand, for mirror-like surface, like ideally speculated reflection, in this case, the p scatter matters more because the scattering direction nearly one. Because in the specular reflection, when we shoot the ray on the surface, it only just go out the exactly one outgoing direction when the surface is really ideal. So we added some scattering PDF, which is a virtual function. We have virtual function. We need to add a virtual function because we are using the abstraction of material. So we need to double a scattering PDF virtual function, and we can override it inside. And as you can see, with the scatter direction and unit vector, we taking dot product with is normal on the surface. And this is equal to cosine theta. And if the cosine theta is less than zero, we are going to clamp to the zero. And if it's not, we are going to use cosine theta over pi, exactly same with this derivation. Remember that we got the integral of p scatter over the whole hemisphere, which is equal to cosine theta pi over pi. And for the last, there is a newly changed this set of codes. After we got the scattered the direction, we are using that in the scattering PDF. And by following this equation, where is it? Uh, yes, here, by following this equation, although we are making an assumption that p scatter and the PDF in the denominator is the same in the reimbursement surface, but we're just represent it in the whole effect equation without abbreviation. So this equation is exactly same with these above the mathematical representation. So I think this is end for today's recording, and thanks for watching. Bye bye.